There is a star out there right now crossing the distance from the Earth to the Moon every 2 minutes. Not a spacecraft, not a particle of light, an entire sun moving at 1% of the speed of light, and it is not alone. For 20 years, astronomers catalogued stars moving too fast for our galaxy to hold, and assumed the thrower was the giant black hole at the centre of the Milky Way. Then they ran the flight paths backward. Half of them did not lead there. They led to the galaxy next door, a soft patch of light you can see with your naked eye, converging on a single point that carries the gravity of 600,000 suns and shows absolutely nothing. No glow, no disk, no object of any kind. Just stars, fleeing something that is not supposed to exist. So what is hiding in the galaxy next door? And why is the only proof of its existence the stars running away from it? Get comfortable and let the room grow quiet. Subscribe if you have not already, and stay with us, because by the end of tonight that empty point in the sky will have a mass, an address, and an arrival date. Let's begin. Part 1. The Star That Was Leaving. Right now, as you listen to this, there is a star crossing the outer edge of our galaxy that is never coming back. It is not orbiting, it is not wandering, it is leaving, moving so fast that the combined gravity of 400 billion suns cannot hold on to it. And the strangest part of this story is not the star itself, it is what the star is pointing back at. Because when astronomers finally traced its path, and the paths of the stars like it, the trail did not lead where anyone expected. But we are getting ahead of ourselves. Every good mystery starts with the first piece of evidence, and this one begins on a mountaintop in Arizona, in the winter of 2005, with a man looking at a number that could not possibly be right. It is a quiet night at the MMT Observatory on Mount Hopkins, about an hour south of Tucson. An astronomer named Warren Brown is working through a stack of fresh spectra, the stretched-out rainbow fingerprints of faint blue stars collected by the big 6.5-metre telescope above him. The control room hums, the screens glow. This is routine work, the kind of patient cataloguing that fills most nights in astronomy. He is measuring velocities, one star at a time, the way you might check items off a list, and then one of them comes back wrong. The software reports that a faint blue star in the outer halo of the Milky Way is receding at 853 kilometers per second. Brown does what any careful scientist does with a number like that. He assumes it is an error. He checks the calibration. He re-reduces the data. He looks for a glitch in the instrument, a cosmic ray on the detector, a mismatched reference line. Any of the ordinary ways a measurement goes bad, the number holds. He runs it again. It holds again. Somewhere out there, roughly 200,000 light-years away, a smudge of blue light is doing something no star had ever been seen doing. It is escaping the galaxy. To understand why that number stopped him cold, you need to know what it takes to leave the Milky Way. Every object in the galaxy sits inside an enormous gravitational well, like a marble resting at the bottom of a bowl the size of 100,000 light-years. To climb out of that bowl from our neighbourhood, a star needs to be moving at roughly 550 kilometers per second. That is the escape velocity. The same idea that governs a rocket leaving Earth, just scaled up to something monstrous. Fall short of that speed and you can climb as long as you like. Gravity will slow you, stop you, and reel you back in. Exceed it, and the galaxy has lost you forever. Your orbit stops being a loop and becomes a one-way road. Nearly everything we had ever measured, hundreds of thousands of stars over centuries of astronomy, was bound. Every star in every catalogue was, in the end, a prisoner on some closed path around the galactic centre. This star was not. When the geometry was worked out, its speed through the galaxy's rest frame came to roughly 700 kilometers per second, comfortably beyond escape velocity, even after accounting for every uncertainty. The bowl could not hold it. Astronomers gave it a long serial number from the survey that found it, but among themselves they called it something simpler, the Outcast. And the Outcast carried a second surprise, quieter than the first but just as important. It was the wrong kind of star to be where it was. This was a B-type star, young, hot, blue, several times the mass of the Sun. Stars like that burn hard and die young. Their lifetimes run to only a few 100 million years, which in stellar terms is barely an afternoon. But the outer halo of the Milky Way, where the Outcast was found, is a retirement community. It is old, thin, and quiet, with essentially no gas left for making new stars. Nothing young should live there, for the same reason you do not find fresh footprints in concrete that set 1 billion years ago. A young star that far out could not have been born there. It had to have been born somewhere busy, somewhere with gas and youth and crowded stellar nurseries, and then it had to travel. And here is where the built-in stopwatch comes in, one of the most elegant tricks in this whole story. Because a star's mass tells you its lifespan, every star carries its own expiration date. The outcast clock allowed it only a few 100 million years of life in total. For it to be so far out in the halo, moving so fast, its journey had to fit inside that lifetime. Work the arithmetic backward and there is only one reading. This star was launched recently and violently from somewhere dense, and it has been climbing away ever since. One star could be a fluke. Nature does occasionally produce a coincidence and dare you to build a theory on it. So Brown and his colleagues, Margaret Geller and Scott Kenyon of the Smithsonian Astrophysical Observatory, did the unglamorous thing. They went looking for more. Night after night on the MMT, year after year, they surveyed faint blue stars across the northern sky's halo, taking spectra, measuring speeds, discarding the ordinary and keeping the impossible. The impossible kept showing up. Another unbound blue star, then another, some receding at 600 kilometers per second, some at 700, one clocked at more than 1,000. Over the following decade, the survey assembled a collection that would become the reference sample for an entirely new class of object. 21 B-type stars, scattered through the outer halo between roughly 160,000 and 300,000 light-years out, every one of them moving too fast for the galaxy to keep. Astronomers named the class hypervelocity stars, and the name is honest. These are not the modest runaways that drift out of star clusters at a few tens of kilometers per second. These are stars with several times the mass of the Sun moving at speeds we normally associate with the debris of exploding stars. Intact, healthy suns, some of them very likely carrying their own planets, headed into intergalactic darkness with no return ticket. Sit with that image for a moment, because it deserves it. Somewhere tonight, a star with maybe 3 times the Sun's mass is crossing the halo above the galactic disk, and if you stood on a world in orbit around it, you would see the entire Milky Way behind you, tilted and receding. 100 billion stars slowly shrinking into a single glowing coin of light. Ahead of you, nothing, black in every direction, forever. That is the destination every hypervelocity star shares. The physics of their exits differ, as we'll see, but the itinerary is identical. Out, alone, for good. But an exit this violent demands an explanation, and in 2005 nobody watching those first measurements could say what it was. Think about what it takes. You cannot throw a star with an explosion alone. A star is not a bullet. It is a furnace the size of 1 million Earths, and most things powerful enough to accelerate it that hard would simply tear it apart. Whatever launched these stars did so while leaving them intact. No scorching, no disruption, no visible trauma at all. The Outcast and its siblings are, by every spectroscopic measure, completely ordinary B-type stars. Ordinary, except that something reached into the galaxy, selected them, and hurled them out at 0.5% of the speed of light without leaving a mark. Here is the part that still gives this story its shape. The answer to that question already existed. It had been sitting in the scientific literature for 17 years, published, peer-reviewed, and almost completely ignored. In 1988, a physicist at Los Alamos National Laboratory had worked out, with nothing but pencil and paper celestial mechanics, exactly how a galaxy throws a star away. He had predicted the speeds. He had predicted the kind of star. He had even predicted what finding one would prove, and what it would prove was the existence of something enormous and invisible. When the Outcast finally appeared, it matched his forecast the way a criminal matches a sketch drawn 2 decades before the crime. So before we follow the runaways any further, we need to go back and read the paper nobody read, because everything that follows, including the discovery that overturned all of it, rests on the strange, beautiful mechanism it describes. Part 2, the prediction nobody read. In 1988, a physicist named Jack Hills was working at Los Alamos National Laboratory in New Mexico, thinking about what happens when stars stray too close to something they should never approach. Los Alamos is famous for other kinds of physics, but Hills was interested in a purely celestial problem, the kind you can state in one sentence, and then spend a career unpacking. The sentence is this: what happens when a pair of stars falls toward a massive black hole? Not a single star, a pair. That distinction turns out to be everything, and it is worth slowing down to see why, because the mechanism Hill's worked out is one of those pieces of physics that feels almost like a magic trick once you see it. Start with the pair. Roughly half the stars in the sky are not single, like our Sun, but binary. Two stars locked in orbit around each other, sometimes separated by less than the distance from the Earth to the Sun, waltzing around a shared centre of gravity for billions of years. A binary is a system with energy stored in it, like a wound spring. The two stars carry enormous speed in their mutual orbit, but it is speed spent going in circles, bound up, going nowhere. Now take that wound spring and let it drift, over millions of years, on an unlucky path toward the centre of its galaxy, toward a massive black hole. A black hole does not reach out and grab things. Its weapon is subtler: tides. The same effect that lets our small moon lift entire oceans works near a black hole with obscene strength, because gravity weakens with distance, and close to something so massive, the difference in pull between near side and far side becomes violent. Approach with a binary, and at some critical distance the black hole pulls on the nearer star measurably harder than on the farther one. The spring is stretched. The two stars, partners for perhaps 1 billion years, feel the black hole's grip more strongly than they feel each other, and at the moment of closest approach, the waltz is over. The binary is torn in two. Here is the trick. Energy has to be conserved. All that speed the pair carried, their orbital motion around each other, plus the enormous velocity of their infall, must go somewhere. What happens, in the clean mathematics Hills wrote down, is a trade. One star loses. It is captured, dropped into a tight, scorching orbit around the black hole, bound to circle it for ages, a permanent hostage. The other star wins more than it could ever win anywhere else in nature. It absorbs the difference. The hostage's forfeited energy is transferred to it in a single gravitational transaction, and it departs the encounter at a speed that has no business belonging to a star. Hills ran the numbers and found ejection velocities that could reach several thousand kilometers per second. No explosion, no contact, no damage of any kind. The escaping star is untouched, unheated, unmarked, flung by pure geometry, like a stone from a sling, except the sling is a dent in space-time, and the stone weighs as much as 3 suns. The mathematics even tells you how hard the throw will be, and the logic is worth carrying with us, because it becomes a fingerprint later in this story. The ejection speed starts with how fast the two stars were circling each other. The tighter the binary, the faster the waltz, and the faster the waltz, the harder the throw. Then the black hole's mass acts as an amplifier. The heavier the hole, the steeper its tides, and the more of the hostage's energy gets handed to the escapee. A binary that orbits itself at 100 kilometers per second can leave the encounter with one member moving at 10 times that, which means the speeds of a galaxy's runaway stars are not random. They are a measurement in disguise. Fast ejections testify to a heavy launcher. Gentler ejections testify to a lighter one. Weigh the exits, and you have weighed the thing at the centre, without ever pointing a telescope at it. Hold on to that idea. In about 20 years of story time, it is going to weigh something nobody has ever seen. And Hills understood immediately what such a star would mean if anyone ever found one. A stone tells you about the sling. A star moving at 1,000 kilometers per second cannot be produced by ordinary stellar neighborhoods. It requires tides steep enough to rip a binary apart, and only one kind of object packs that much gravity into that little space. Find a hypervelocity star, trace its path backward, and at the starting point of that path there must sit a massive black hole, whether or not you can see one there. The runaway star, Hills realized, is a detection. It is evidence that survives, travels and testifies long after the encounter, far from the scene. He published the prediction in 1988, and then, for 17 years, almost nothing happened. The paper sat in the literature the way a bell sits in an empty church. No instrument on Earth could find the stars it described, and predictions that cannot be tested have a way of being politely forgotten. Then came the winter of 2005, the mountaintop in Arizona, and the number that would not go away. The outcast was everything Hills had ordered in advance. A B-type star, intact and unmarked, exceeding galactic escape velocity, at a distance consistent with a launch from the centre of the Milky Way a couple of 100 million years earlier. The sketch matched the suspect, and our galaxy had a suspect already in custody because by 2005, astronomers were closing in on the object at the Milky Way's exact centre, a radio source called Sagittarius, a star, compact, dark and heavy. Two teams, led by Reinhard Genzel and Andrea Ghez, had spent years tracking individual stars whipping around that unseen point. One of those stars, called S2, completes a full orbit every 16 years, at speeds reaching several thousand kilometres per second, around something that emits almost no light yet weighs 4.3 million suns. That work would eventually earn the 2020 Nobel Prize in Physics, and it certified the Milky Way's central black hole beyond reasonable doubt. Notice something lovely here. Those tight-orbiting S-stars are exactly the hostages Hills predicted, the captured halves of shredded binaries, still circling the object that took them. The prisoners and the escapees are two halves of the same crime, and we can observe both. The confirmation kept improving. In 2019, a survey turned up the cleanest single piece of evidence the mechanism has ever produced. A star designated S5HVS1, an A-type star in the southern sky, moving at 1,755 kilometers per second, at the time the fastest main-sequence star ever measured. Its trajectory was precise enough to run backward like a film in reverse, and the film ended exactly at Sagittarius A star, about 4.8 million years ago, not near the centre, at it. Here was a star observed in the act, mid-flight, with the launch site identified beyond argument. The Hills mechanism was no longer a proposal. It was a documented behaviour of our galaxy's black hole. And so a comfortable picture settled over the field, the kind of picture that gets drawn in textbooks and repeated in lectures until it hardens into furniture. Hypervelocity stars come from the galactic centre. Sagittarius, A star, is the engine. Every unbound blue star in the halo is a former binary partner, launched from the heart of the Milky Way, and if you trace any of them backward you will find the same address at the end of the line. It was clean, it was confirmed, and it lasted about 20 years. To be fair, astronomers knew all along that nature had lesser ways of hurrying stars. A supernova in a tight binary can release its companion like a stone from a snapped rope. That channel is real, and it produced the star US 708, a stripped helium star crossing the galaxy at 1,200 kilometers per second after its white dwarf partner detonated. Crowded newborn clusters can eject members through gravitational roughhousing. 3 stars tangle, one gets thrown out the door. But both channels have well-understood ceilings. For a massive intact B-type star, they struggle to produce much beyond a few hundred kilometers per second, and they scatter their products randomly in every direction with no preferred origin. They are pickpockets. The Hills mechanism is the only natural process that operates like a cannon, and cannons, unlike pickpockets, leave a trail you can follow home. But notice the quiet assumption holding up the entire picture, the one almost nobody thought to question. Tracing a star backward requires knowing its full motion in 3 dimensions. A spectrum only gives you one of those dimensions, the speed along your line of sight, toward you or away. The other 2, the star's sideways drift across the sky, are almost immeasurably small. For a star 100,000 light-years away, its sideways motion shifts its position each year by an angle comparable to the width of a coin viewed from another continent. In 2005, no instrument on Earth could measure that. So when astronomers said the runaways came from the galactic centre, they were not reporting a measurement. They were reporting an assumption. The centre was simply the only cannon anyone knew about. Every trajectory had been drawn through it, because every trajectory had to be drawn through somewhere. For the assumption to be tested, someone would have to measure the sideways motion of faint stars at intergalactic distances, a precision so absurd it sounds like satire, which is exactly what a spacecraft the size of a small truck, parked 1 million miles behind the Earth, was quietly built to do. Part 3. The Machine That Measured the Sky. On December 19, 2013, a Soyuz rocket lifted off from French Guiana carrying one of the most consequential machines Europe has ever built, and one of the least famous. It carried no astronauts. It took no pretty pictures. Most people have never heard its name. The spacecraft was called Gaia, and its job description fits in a single line: measure the position of everything. Gaia was sent to a place called the second Lagrange point, about 1 million miles from Earth on the side away from the Sun. the same quiet gravitational parking spot where the James Webb Space Telescope now sits. From there, spinning slowly and continuously, it swept its twin telescopes across the entire sky, over and over, for more than a decade. The science Gaia performs is called astrometry, and it is the oldest job in astronomy. Older than telescopes, older than physics. It is the business of writing down exactly where things are. Ancient astronomers did it with sighting rods and stone circles. What Gaia brought to this old business was precision of a kind that is genuinely hard to hold in your head. For its well-behaved stars, Gaia could pin a position to within about 24 microarc seconds. Numbers like that mean nothing without a picture, so here is the standard one, and it is worth pausing on. That is the precision needed to stand in New York and measure the width of a single human hair lying on a sidewalk in Los Angeles. Not to see the hair, to measure its width. Now do that 2 billion times. Over 10 years, Gaia catalogued nearly 2 billion stars, visiting each one an average of 70 times, watching how every single point of light drifted year over year against the deeper sky. It helps to picture how the machine actually did this, because the method is almost absurdly patient. Gaia carried 2 telescopes pointed at widely separated patches of sky, feeding a single camera of nearly 1 billion pixels, for years the largest digital camera ever flown. As the spacecraft rotated once every 6 hours, stars from both patches drifted across that camera in a slow procession, and Gaia timed each crossing to 1/millionth of a second. Position, for Gaia, was time. Do that for the same star 70 times across a decade, from opposite sides of Earth's orbit, and 2 tiny motions fall out of the arithmetic. One is parallax, the star's apparent annual wobble as Gaia's viewpoint swings around the Sun, which gives you the star's distance directly, the way your thumb seems to jump against the background when you blink one eye and then the other. The other is proper motion, the star's true sideways drift through the galaxy. Distance and drift for 2 billion stars. That is the entire treasure, and it is the only treasure this story needs. That drift is the treasure. Remember the missing dimension from the end of our last chapter. When astronomers found the first hypervelocity stars, they could measure only the motion along the line of sight, the speed at which a star approaches or recedes, read from the stretching of its light waves. That is 1 dimension out of 3. The other 2 make up what astronomers call proper motion, the star's sideways slide across the sky. For nearby stars, proper motion is measurable with patience. For a faint blue star 200,000 light-years away, the sideways slide in a full year is comparable to watching a coin on the moon shift its position by a fraction of its own width. Before Gaia, writing down such a number was fantasy. After Gaia, it was a catalogue entry. And with all 3 dimensions of a star's velocity in hand, you can do the thing this entire story turns on. You can run the film backward. You take the star's position, reverse its velocity, add a model of the galaxy's gravity and integrate, step by step, millions of years into the past, until the trajectory tells you where the star came from. Astronomers do this routinely now. It is celestial forensics. Every runaway drew a chalk line across the sky as it fled, and Gaia made the chalk visible. Gaia's results did not arrive as one announcement. They arrived as data releases, enormous public catalogues, each one more precise than the last, dropped onto the world's astronomers like a slow series of controlled detonations. Data Release 2, in 2018, rewrote whole subfields within months. Data Release 3, in 2022, sharpened everything again. The release this story depends on. Each time, thousands of researchers dove in, and each time familiar objects began behaving unfamiliarly. Stars believed for decades to be neighbours turned out to be passing strangers. Clusters dissolved. Streams of stars appeared across the halo, revealed as the shredded remains of small galaxies our Milky Way consumed billions of years ago. It is one of the strange truths of modern astronomy that a spreadsheet can be more revolutionary than any photograph, and Gaia's spreadsheets redrew the entire neighbourhood, and buried in that redrawing there was an early warning shot, a single star that should have told everyone what was coming. It was one of the classic hypervelocity stars, the third ever found, discovered back in 2005 and known as HVS-3. From the beginning, HVS-3 had a problem that polite papers kept flagging in careful language. Its clock did not balance. Run the arithmetic assuming it was launched from the centre of the Milky Way, and you get a flight time of well over 100 million years, but the star's mass gives it a total lifespan shorter than the journey. A star cannot spend more time travelling than it has been alive. It was as if a letter had arrived postmarked before the sender was born. For over a decade, astronomers proposed workarounds. Maybe it was a rejuvenated merger of two older stars, they suggested, a stellar collision wearing a young star's face. The workarounds were clever, and none of them felt clean. Then, in 2019, a team led by Douglas Boubert and Dennis Urquhart took Gaia's fresh proper motions for HVS-3 and ran the film backward properly for the first time. The trajectory did not pass anywhere near the centre of the Milky Way. It came sweeping in from the south, out of a small companion galaxy, the Large Magellanic Cloud. The travel time worked. The clock balanced. The letter had simply been mailed from a different address. Even before that result, the theorists had laid the trap. In 2016, Boubert and N. Wynne Evans published a prediction with the same quiet audacity as Hill's paper from 1988. If the Large Magellanic Cloud carries a massive black hole at its centre, then the Hill's mechanism must be running there too, and the cloud must be spraying hypervelocity stars of its own. But there was a twist. The cloud is not stationary. It is orbiting the Milky Way at roughly 300 kilometers per second. Stars flung forward from a moving platform inherit its motion, so the cloud's escapees would not scatter evenly across our sky. They would pile up, concentrated in one particular direction, toward the constellation Leo. It was a precise, falsifiable forecast. A hidden black hole in the galaxy next door would announce itself as a traffic pattern. Gaia itself did not live to see the question settled. On January 15th, 2025, after 11 years of continuous scanning, the spacecraft's sky survey ended. Its cold gas fuel was nearly spent. That March, controllers commanded it into a retirement orbit and switched it off. A strange, tender moment in spaceflight, engineers saying goodbye to a machine that had quietly outmeasured every astronomer in history combined. But a mapmaker's death does not erase the maps. The archive remains, still only partly mined, with a final release, Data Release 4, nearly doubling the precision again, expected at the end of 2026. Gaia the spacecraft is a derelict now, looping the sun in silence. Gaia the dataset is still detonating, and it will go on detonating for decades, the way a great library keeps teaching long after its authors are gone. And in 2025, the year the spacecraft went dark, a team of astronomers at the Harvard-Smithsonian Center for Astrophysics decided to aim its finest measurements at the coldest case in the field. 21 unbound B-type stars, the classic sample, the outcast and all its siblings, the stars that had built the entire textbook picture. For 20 years, every one of them had been assumed to come from the center of the Milky Way, because the center was the only canon anyone could name. Now, for the first time, the assumption could simply be checked. 21 films run backward through the galaxy's gravity one by one. The team expected the trajectories to converge on Sagittarius A star like arrows returning to an archer. That is not what the films showed. Part 4. The map points the wrong way. The study that broke the picture was led by a young astronomer named Jiwon Jesse Han, working with colleagues at the Harvard-Smithsonian Center for Astrophysics, the same institution whose survey had discovered these stars in the first place. There is something fitting in that. The people who built the catalogue came back 2 decades later, with better instruments, to check the story the catalogue had been telling. Their method was, in outline, exactly what we have described. Take each of the 21 unbound B-type stars, combine its measured radial velocity with Gaia's Data Release 3 proper motions, and integrate its trajectory backward through a state-of-the-art model of the local gravitational landscape. One detail matters enormously, and it is a mark of how careful this work was. Their model did not include just the Milky Way. It included the Large Magellanic Cloud as well. Its mass, its motion, its gravitational tug on everything passing nearby. Earlier tracebacks had treated our galaxy as if it sat alone in space. This one admitted that we have company, and that the company is heavy enough to bend the evidence. 21 stars, 21 films run in reverse. The expectation, remember, was total convergence. Every arrow flying home to Sagittarius a star, the case sealed for good. Instead, the films split. About 7 of the stars did trace back to the center of the Milky Way. The classic story confirmed for them the Hill's mechanism operating at Sagittarius a star exactly as advertised. A handful were too uncertain to call, and roughly 9 of the 21, nearly half of the sample that could be confidently classified, did not come from our galaxy at all. Their trajectories swept backward, out of the halo, across 160,000 light-years of space, and converged on the Large Magellanic Cloud. It is hard to overstate how disorienting a result like this is for a field, so let it land slowly. For 20 years, these stars had a biography. It was taught in courses, printed in textbooks, drawn in review article diagrams, born near the galactic centre, shredded from a binary partner by our supermassive black hole, flung outward past the Sun's orbit and into the halo. Every one of those biographies had been written with one dimension of the star's motion missing, and for nearly half the sample, the missing dimension changed the ending entirely. These stars were never ours. They are immigrants, arriving from the galaxy next door, passing through our halo on their way to nowhere. The wrong answer had sat unquestioned for 2 decades, not because anyone was careless, but because nobody could measure sideways. And that should raise a small, cold question that extends far beyond this story. How much else in the sky is pointing the wrong way, waiting for its missing dimension to be filled in? And to be clear about what did not collapse, the galactic centre's own record stands. The 7 stars that trace home to Sagittarius A star still trace home to it, and S5 HVS1, the escapee filmed mid-flight with the launch site identified beyond argument, remains the cleanest confirmation the Hill's mechanism has ever had. This is worth saying carefully because science rarely overturns cleanly. The 2025 result did not prove the old story wrong. It proved the old story incomplete. Our black hole is a launcher. It simply turns out not to be the only one in the neighbourhood. The team stress-tested that conclusion in every way the data allowed. They varied the model of the Milky Way's gravity within its uncertainties. They ran the tracebacks with the Large Magellanic Cloud's own gravity included and excluded. They asked whether stars genuinely launched from our centre could be deflected en route into seeming to come from the cloud, and whether ordinary halo stars could masquerade as escapees. The cloud stars stayed cloud stars, short of the measurements themselves being wrong, and they are Gaia's finest. The origin is real. There is an old line worth introducing here, because this entire field has quietly organised itself around it. You can learn a lot about something by watching what runs away from it. It sounds like a joke about bad neighbours. It is actually a precise description of the physics. The runaways carry information out of a place we cannot see into a place we can. Speed, direction, timing, all of it preserved in flight like a message in a bottle. Han's team was, in the most literal sense, reading the mail. And the mail said something nobody was prepared for. Because the 9 cloud stars did not merely point back at the cloud. They arranged themselves, on our sky, into exactly the pattern predicted 9 years earlier. They cluster, tightly, unmistakably, toward the constellation Leo. Remember the forecast from 2016. A black hole in the Large Magellanic Cloud would not scatter its escapees evenly, because the cloud itself is a moving platform, orbiting the Milky Way at roughly 300 kilometers per second. Think of standing on a fast-moving train and throwing baseballs in every direction. The balls you throw forward, in the direction the train is travelling, fly fastest relative to the ground. The train speed adds to your throw. An observer in a field nearby does not see baseballs raining evenly from the sky. They see a stream concentrated ahead of the train. Leo is the patch of our sky that lies ahead of the train. The stars pile up precisely where the cloud's orbital motion says forward-thrown objects must land. Random contamination cannot fake that geometry. Supernova kicks cannot fake it. They fire in all directions. Cluster ejections cannot fake it. Only a launcher riding inside the moving cloud produces that traffic pattern, stamped on our sky like a wake behind a ship. And the stars carried a second fingerprint, quieter but just as damning. Their speeds are wrong in exactly the right way. The escapees that trace back to Sagittarius A* travel on average near 870 kilometers per second. The cloud stars are systematically slower. Most left their galaxy at between 400 and 600 kilometers per second relative to it. Now recall the idea we tucked away in the story of Jack Hill's. Ejection speed is a measurement in disguise. The heavier the black hole, the steeper its tides, and the harder it throws. A lighter black hole throws more gently. If the cloud's escapees were contaminants or flukes, their speeds would scatter without pattern. Instead, the entire population runs slow, as one, the unmistakable signature of a real launcher that is genuinely lighter than ours. The Leo clustering tells you where the cannon is. The speed distribution tells you what the cannon weighs. 2 independent fingerprints, both pointing at the same object. There is even a third fingerprint, one that tends to get lost beneath the first 2 but may be the most quietly persuasive of all, the traffic volume. From the number of escapees caught in one small survey of one slice of sky, you can estimate how often the cloud launches a star, and the answer comes out broadly comparable to the launch rate of Sagittarius A star itself. Sit with how strange that is. A galaxy carrying only a few % of the Milky Way's stars, a passenger galaxy, a smudge in our southern sky, appears to be flinging hypervelocity stars about as often as the 4.3 million Sun monster at the centre of everything. Some of the survey's escapees, stars catalogued from our own halo, assumed for 20 years to be ours, were never even passing through our galaxy's interior at all. They entered the books as Milky Way ejecta, purely because nobody imagined another canon existed, so the team weighed it, feed the observed ejection speeds and arrival rate into the Hills mechanism, and the mathematics returns a mass for the hidden launcher, roughly 600,000 times the mass of the Sun. Set that on the ladder of known black holes, and it occupies a genuinely strange rung. The black holes left behind by dying stars weigh a few suns, a few dozen, at the extreme end perhaps 150. Sagittarius A star weighs 4.3 million. The giant at the heart of the galaxy, M87, weighs 6.5 billion. 600,000 is a middleweight, modest by the standards of galactic centres, yet thousands of times too heavy to be any dead star. It is, on paper, one of the most significant black holes ever identified in our corner of the universe. The nearest massive black hole outside the Milky Way, sitting in plain view of every backyard stargazer in the southern hemisphere. And notice what 600,000 solar masses actually looks like in person, because the intuition matters for everything that follows. A black hole that heavy has an event horizon only a few times wider than the distance from the Earth to the Sun. On a galactic map, that is not a landmark, it is a pinprick. You could hide it inside a single star system, and a passing traveller would notice nothing but darkness. No size, no glow, no silhouette, just a small region where the universe declines to send back any light. The mass of 600,000 suns, folded into a package smaller than the orbit of Jupiter, emitting nothing. Objects like that are not merely hard to find. Unless they are actively feeding, they are very nearly the definition of unfindable. Except for one thing, and it is the thing this entire video turns on. Point any telescope ever built at the place those 9 trajectories converge, and you will find nothing. No brilliant disk of shredded, superheated matter. No X-ray point source burning in the cloud's centre. No radio beacon. No jet. No flare. No measured swarm of stars whipping around an unseen mass the way his 2 whips around Sagittarius A star. Every instrument comes back with the same report: empty sky. The object that 4 separate lines of evidence agree must exist. The tracebacks, the Leo clustering, the speed fingerprint, the ejection rate, has never once been observed. Its entire existence is written in the handwriting of the stars that fled it. We have, in effect, discovered a monster by interviewing its refugees. And before we go hunting for the monster itself, we should get to know the crime scene, because the galaxy those stars are fleeing is one of the strangest, most spectacular objects in the entire southern sky, and it has been hiding its secrets in plain sight for as long as humans have been looking up. Part 5. The Scene of the Crime. If you stand under a dark sky anywhere in the southern hemisphere, rural Australia, the Chilean high desert, a beach in South Africa, and let your eyes adjust, you will see it without any equipment at all. Off to one side of the Milky Way's great band, there is a soft glowing patch, about the size of 20 full moons laid side by side. It looks like a piece of the Milky Way that broke off and drifted away, a cloud that never moves and never dissolves. People have been watching it for as long as people have been in the southern hemisphere. Polynesian navigators steered by it and read weather omens into it. Aboriginal Australian traditions, some of the oldest continuous astronomical knowledge on Earth, gave it stories and names tens of thousands of years before the invention of writing. Europe learned of it when the survivors of Ferdinand Magellan's expedition came home in 1522 and described 2 luminous clouds in the alien southern sky. The name stuck: the Magellanic Clouds, large and small. And for most of history that is all they were, beautiful smudges. Only in the 20th century did astronomers establish the truth. The Large Magellanic Cloud is not a cloud at all. It is an entire galaxy, our nearest major companion, and every one of those 9 runaway stars traces back into that soft glowing patch your naked eye can see. Let us get its measure. The Large Magellanic Cloud sits about 160,000 light-years away, close as galaxies go. The light reaching your eye tonight left it when early humans were first experimenting with stone tools. It spans roughly 32,000 light-years, perhaps a third the width of the Milky Way's disk, and it carries a few billion solar masses of stars, only a few % of our galaxy's stellar population. But stars are not the whole story. Weigh the cloud properly, including its halo of dark matter, and most modern estimates land between 10 and 20% of the Milky Way's total mass. That number surprised nearly everyone when it firmed up over the last decade. The cloud is not a satellite in the way a pebble is a satellite of a mountain. It is more like a companion in the way a large dog is a companion, small compared to you, but very much capable of pulling on the leash. Keep that in mind, because the pulling matters later in our story, and whatever you do, do not mistake it for a quiet retirement community. The Large Magellanic Cloud is one of the most furiously productive star factories in our entire corner of the universe. Its crown jewel is the Tarantula Nebula, a sprawling region of glowing gas also known as 30 Doradus, the single most intense star-forming region in the whole local group of galaxies, ours included. Nothing in the Milky Way today comes close. At the Tarantula's heart sits a cluster called R136, packed with the most extreme stars ever weighed, including R136A1, the reigning heavyweight champion of known stars, roughly 200 times the mass of the Sun, burning millions of times brighter. If the Tarantula sat where the Orion Nebula sits in our sky, it would cast shadows at night. This little galaxy builds giants. The clouds have also mattered to science far beyond their own borders, in a way worth a brief detour, because it shows how long this little galaxy has been quietly teaching us. In the early 1900s, an astronomer at Harvard named Henrietta Leavitt was cataloguing thousands of variable stars in the Magellanic Clouds, stars that brighten and dim on regular schedules. Because all the stars in a cloud sit at essentially the same distance from us, Leavitt noticed something no one could have seen in our own scattered galaxy. The slower a variable star's rhythm, the brighter it truly was. That simple relationship became the first reliable ruler for measuring distances beyond the Milky Way. It is the discovery Edwin Hubble later used to prove other galaxies exist at all, and then to find that the universe is expanding. Follow the chain of modern cosmology backward far enough, and it rests on careful measurements of the galaxy next door. The cloud calibrated our entire map of the cosmos, which lends a certain irony to the discovery that we may have missed a 600,000 sun object sitting inside it the whole time. It performs in other ways too. In February of 1987, a point of light flared in the cloud's outskirts, and within hours became visible to the naked eye, a star ending its life in a supernova. Supernova 1987A was the closest observed stellar explosion in almost 4 centuries, close enough that detectors buried in mines on Earth caught 24 ghostly neutrinos from the collapsing core, the first time humanity ever received particles from the interior of a dying star. Astronomers have watched its expanding wreckage evolve in real time ever since, like ecologists monitoring a forest fire from above. When something dramatic happens in the nearby universe, there is a good chance it happens in the Large Magellanic Cloud. This is simply an eventful galaxy, which makes the silence at its centre, the silence we are heading toward, all the more wrong. The cloud is also not travelling alone, and it is not travelling calmly. It moves in close company with the small Magellanic Cloud, its lesser sibling, and the two of them have been brawling for at least the better part of 1 billion years. Somewhere between 150 and 250 million years ago, they appear to have collided outright, the small cloud ploughing through or past the large one, gravitationally churning both, and both together are falling toward us. Stretched behind them across more than half the southern sky runs one of the great unseen structures of the local universe, the Magellanic Stream, an enormous ribbon of hydrogen gas, roughly 500 million suns worth, torn loose from the clouds and left trailing like smoke behind a moving fire. You cannot see it with your eyes, it glows only in radio wavelengths, but it is the plainest possible evidence that the clouds are being actively worked over by gravity, shedding material as they come. Most modern models agree on something remarkable. This is likely the Large Magellanic Cloud's first close pass around the Milky Way. It is not a long-term resident on a settled orbit. It is a newcomer arriving now in the middle of its first real encounter with a galaxy 10 times its size. That first passage picture, incidentally, is why the cloud's total weight remained controversial for so long. A satellite that has looped a big galaxy many times gets progressively stripped and lightened, while a first-time visitor arrives still carrying its full dark matter luggage. The measurements that finally tipped the debate, including the sheer gravitational disturbance the cloud is inflicting on the Milky Way's outskirts, wakes and warps our surveys can now actually map, all point the same way: heavy, intact, and arriving for the first time. We are not watching a long-time companion on a settled circuit. We are watching first contact between two galaxies, in progress, from the inside. All that violence has left the cloud visibly dishevelled, and here the details start bearing directly on our mystery. The Large Magellanic Cloud has a strange lopsided anatomy. It has a bright central bar of stars like many galaxies, but the bar is off-centre. Its disk is warped and tilted, and when astronomers try to answer the simplest possible question about it, where is the middle? The galaxy refuses to give one answer. The centre you would draw by eye, the brightest concentration of starlight, is in one place. The centre of its rotating hydrogen gas is somewhere else. The centre that its stars actually orbit, the dynamical centre, appears to be somewhere else again. These centres miss each other by noticeable margins, in some measurements, by more than 1,000 light-years. Our own galaxy is not like this. Everything in the Milky Way agrees on where the middle is, and Sagittarius A star sits precisely there. The cloud is a galaxy whose own contents cannot agree on where its heart is. Now bring the runaway stars back into the picture. When the tracebacks are examined closely, the 9 trajectories do not converge on the cloud's bright photometric centre, the middle you would pick by eye. They converge on a point offset from it by roughly 1.2 degrees on the sky, over 3,000 light-years at the cloud's distance. In an orderly galaxy, that mismatch would be a problem for the whole theory. In this dishevelled, collision-scrambled galaxy, it is almost a point in the theory's favour. The launch point falls in the disturbed zone where the cloud's true dynamical centre plausibly hides, off-centre, like everything else about it. The stars are not pointing at the place we assumed was the middle. They may be telling us where the middle actually is, marking, with their departures, the gravitational anchor of the entire galaxy, a spot on the map with nothing visible on it. One more detail completes the scene. Gaia did not only track the stars that left the cloud long ago, it tracked thousands of massive stars still inside it. Among them, astronomers keep finding runaways, dozens of O and B stars moving fast enough to escape the cloud entirely. That bar is low. The cloud's escape velocity is only about 90 to 150 kilometers per second, gentle compared to the Milky Way's 550. Most of these internal runaways are easily explained, kicked out of crowded newborn clusters through ordinary gravitational roughhousing. But the extreme tail of that population is not easily explained, and one member of that tail is so far beyond every natural ceiling that it deserves, and will get, a chapter of its own. Before that, though, we need to walk to the offset point ourselves. 9 trajectories converge on a patch of empty-looking sky inside the galaxy next door. It is time to stand there, look around, and confront what is, and is not, waiting at the crime scene's exact address. Part 6. The Invisible Monster. So come stand at the address. Imagine yourself suspended in space, far inside the Large Magellanic Cloud, at the exact point where the 9 trajectories cross, the offset point, a degree and change from the bright centre, the spot the fleeing stars keep pointing back toward. Look around you. In every direction the sky is crowded beyond anything visible from Earth. Sheets and rivers of stars, blue, white and gold, run to every horizon. Off in one quarter hangs the Tarantula Nebula, a glowing thundercloud hundreds of light-years across, lit from inside by newborn giants. The combined shine of a few billion suns washes through this place. It is, by any human standard, one of the most crowded, luminous neighbourhoods in the nearby universe. Now look at the one place the trajectories converge, the point every fleeing star's path crosses, the centre of the crime. There is nothing there, no glow, no disk, no point of a light stranger than its neighbours, no visible distortion, no shadow, no silhouette, just ordinary starfield, indistinguishable from the starfield beside it. You could drift through this exact position and never know it was the most important address in the galaxy. Somewhere within reach of this spot, if the evidence is right, sits the mass of 600,000 suns, and it is presenting perfectly as nothing at all. How can that be? How does something that heavy hide in the middle of a galaxy we can see with our naked eyes? The answer starts with correcting the most common misconception in all of popular astronomy. Black holes do not shine, but almost every black hole you have ever seen an image of was shining brilliantly. The glow never comes from the hole, it comes from the meal. When gas, dust, or a shredded star spirals inward, it crowds into a whirling disk, rubs against itself at ferocious speed, and heats to millions of degrees. Matter about to disappear announces itself with some of the brightest light in the universe. Every famous black hole is famous because it is eating, but starve a black hole, set it in a region with no infalling gas, no doomed companion star, nothing on the menu, and the fire goes out completely. What remains is blackness against blackness. No surface to reflect light, no heat to radiate. A starved black hole is not merely dim. It is arguably the darkest kind of object the universe can manufacture. Silence is not evidence against a black hole. Silence is a black hole's natural state, and the mealtimes are genuinely rare. For a black hole like this one, the most dependable food delivery is an unlucky star wandering close enough to be torn apart and swallowed. An event astronomers estimate happens for a typical galaxy's central black hole, perhaps once every 10,000 to 100,000 years. Between meals, even a hungry monster produces almost nothing. Run the numbers on the thin gas actually available near the cloud's centre, and a 600,000 sun black hole grazing on it would glow more faintly than a single bright star at that distance. One unremarkable point among millions. We are not failing to see a bonfire. We are failing to pick out one dark ember in a field of lit candles during a fast that may already be 100 centuries old. Still, surely you might think we have other tools. We do, and it is worth watching each one fail in turn, because the pattern of failure is the shape of the problem. X-rays. Whenever black holes feed even modestly, the innermost hottest gas announces itself in X-rays, and orbiting observatories like Chandra have mapped the Large Magellanic Cloud repeatedly. The cloud is full of X-ray sources, feeding stellar mass black holes and neutron stars in binaries, but at the offset point, no obvious source of the right kind stands out. Radio. Supermassive black holes sipping even thin gas often hum in radio wavelengths as Sagittarius A star does. No such compact hum has been identified there either. Jets, flares, outbursts, nothing on record. Then there is the most direct method in the book, the one that convicted our own galaxy's black hole. Watch the stars closest to it. Any mass that large rules a small kingdom, a region where its gravity dominates over the galaxies, called its sphere of influence. Stars inside that kingdom orbit visibly faster the closer they are, and mapping their speeds weighs the invisible king, as S2's frantic 16-year orbit weighed Sagittarius A star. But mass sets the kingdom's size, and 600,000 solar masses rules only a few light years. At the cloud's distance seen from Earth, a few light years shrinks to an angle so small that picking out individual orbits within it strains even our best current instruments, especially in a field that crowded with no beacon marking which stars to watch. The kingdom is real, but from 160,000 light-years away, it is smaller than our ability to check. Every tool in the kit returns the same verdict, not detected, which frustratingly is exactly what this theory predicts. A starved middleweight in a crowded, dusty, scrambled galaxy should look like nothing. The monster's invisibility is not a hole in the case, it is a property of the suspect. And here the story widens because a black hole of this particular weight would be precious far beyond the cloud itself. Astronomy has a strange, persistent gap running through its black hole census, and 600,000 solar masses sits right at the edge of it. On one side of the gap live the black holes made by dying stars. A few solar masses, a few dozen, topping out somewhere near 150. We have found those by the dozens. On the far side live the giants in galactic centres, millions to billions of solar masses. We have weighed those across the universe. In between stretches a strange near emptiness spanning the hundreds, the thousands, the tens and hundreds of thousands, the intermediate mass range where confirmed detections are so scarce that each candidate becomes a small celebrity. The gap is almost certainly not real emptiness. To grow the giants at all, the universe presumably had to pass through these middleweights. They should exist in quantity. We simply cannot see them, because a middleweight is heavy enough to be rare and quiet, yet too light to rule a kingdom big enough to spot from far away. The middle of the census is missing for the same reason the cloud's centre looks empty. The tools only see the loud. The few candidates we do have only sharpen the point. An object called HLX-1, in a galaxy 300 million light-years away, flared in X-rays with a brightness suggesting around 20,000 solar masses, caught only because it happened to feed while we happened to watch. Gravitational wave detectors heard two large black holes collide in an event called GW 190521, welding together into a hole of roughly 140 solar masses, a middleweight being born, audible only in the final second of the merger. Notice the pattern. We catch the middle class only in moments of violence. The quiet majority, the ones simply sitting in dwarf galaxies doing nothing, have no census at all, and simulations of galaxy growth predict something more unsettling still. Our own halo should be scattered with dozens, perhaps hundreds, of leftover massive black holes from all the small galaxies the Milky Way has consumed, each one dark, dietless, and adrift. The graveyard is presumably full. We have simply never been able to read the headstones. When astronomers have managed to catch a middleweight, notice how they did it. In 2024, a team studying the Great Globular Cluster Omega Centauri, a glittering ball of 10 million stars, and very likely the stripped, stolen core of a small galaxy the Milky Way devoured long ago, found a handful of stars near its centre moving too fast to stay put unless something unseen anchors them. The verdict? A black hole of at least 8,200 solar masses, betrayed by fast stars. The same year, Gaia's data revealed a 33 solar mass black hole under 2,000 light-years from Earth, completely dark, completely quiet, because a companion star's path wobbled around an unseen partner. Every quiet black hole we have ever found, we found the same way, not by seeing it, but by noticing what moves strangely near it. Motion is the only language a dark object speaks. The Large Magellanic Cloud's candidate fits the pattern perfectly. It is just being read at longer range, through the motion of stars that already left. If you want reassurance that invisibility is a normal phase of this business, look at the most certified black hole in the universe. Sagittarius A star entered the record in 1974 as nothing but a compact crackle of radio noise at the galaxy's heart. For decades, its black hole identity was an inference, argued from motion, doubted in seminars, hedged in review articles. The stellar orbit campaigns of the 90s and 2000s made the inference overwhelming. But the object itself was not actually imaged until 2022, when the Event Horizon Telescope released its portrait, a glowing ring around a dark centre. Nearly half a century passed between first evidence and first sight. The cloud's candidate, if real, is simply early in that same long corridor, inferred, contested, unphotographed. With one great disadvantage: it may have nothing to photograph. No feeding, no ring, no fire, only the refugees. One more implication, and it may be the biggest in this chapter. Across the universe, black hole mass tracks its host galaxy. Bigger galaxies, bigger central black holes, following scaling relations astronomers have measured for decades. A 600,000 sun black hole in a galaxy, the cloud's size is not an outlier. It is almost exactly what the scaling relations predict. Now follow that thought to its uncomfortable end. There is nothing special about the Large Magellanic Cloud. The universe holds more dwarf galaxies than any other kind. They outnumber the giants many times over. If this perfectly ordinary dwarf carries a sleeping central black hole, then dwarf galaxies as a class plausibly carry them, and the universe contains billions of massive black holes that no census has ever counted. Dark and dietless, detectable only if something happens to run away from them. The cloud's monster would not be an exception. It would be the first entry in a ledger we have never once opened. And yet, even granting all of it, the hidden middleweight, the offset centre, the gentle 400 to 600 km per second throws it explains so well, there remains one object in this story that it cannot comfortably explain. One star, flagged in the cloud's own neighbourhood, moving so fast that even a hidden monster begins to look insufficient. It is time to talk about the outlier. Part 7. The Star That Breaks the Ceiling. Among the fast stars associated with the Large Magellanic Cloud, one candidate stands so far above the rest that it forces a different kind of conversation. It is a B-type star, the same hot, blue, several solar mass class as the classic runaways, flagged in Gaia-era data near the cloud, with a measured sideways motion that converts, at the cloud's distance, to a speed in the neighborhood of 3,200 kilometers per second. Say that number slowly. 3,200 kilometers every second. That is roughly 1% of the speed of light. Not a particle, not a fragment of an explosion, an entire star, a furnace wider than 1,000,000 Earths, possibly with planets, moving at a percent of the fastest speed the universe permits anything to move. Let us be honest before we are amazed, because this is exactly the kind of number that demands honesty first. It comes with an asterisk. The measurement is a candidate, not a certainty. Speeds like this live or die on tiny quantities, a proper motion here, an assumed distance there. And the history of extreme velocity claims is littered with stars that slowed down dramatically once better parallaxes arrived. Astronomers have been burned enough times to build a reflex. Flag it, publish the caution, wait for the next data release. That is where this star sits tonight. Flagged, extraordinary if true, and awaiting its verdict. But the reason it belongs in this story is what happens if it holds. Because if that speed is real, it does not just stretch the natural explanations we have been building, it breaks through their ceiling entirely. First, feel the speed. Earlier we planted a phrase, Earth to the moon in 2 minutes, and it is time to cache it properly, because said quickly it slides past you, so ride along. Imagine you could stand on a platform in space beside this star and travel with it. The moon's distance from Earth, the farthest any human being has ever travelled, a gulf that took the Apollo astronauts 3 days to cross, unspools beneath you in about 120 seconds. 2 minutes, and you have covered the entire span of human exploration. Keep riding. The distance to Mars at its closest, a journey our best spacecraft needs 7 months to make, passes in under a day. The gap between the Sun and the Earth, 93 million miles, takes you about 8 hours. Sunlight itself only beats you by a factor of 100. In a matter of weeks you cross the span of the entire planetary solar system. Every distance that defines human spaceflight, every gulf we measure our ambitions against, collapses at this speed into afternoons and errands. And now do the one thing the speed cannot survive. Lift your eyes. Ahead of you, the nearest galaxies hang in the darkness, and at 3,200 kilometers per second, the nearest of them is still a journey of tens of millions of years. The grand ones, hundreds of millions. Ride the fastest star in this story, and the universe is still, for any practical purpose, out of reach. That is the true size of the map we live on. A speed that humbles every machine our species has ever built is a rounding error against the space between galaxies. It is worth appreciating, too, what kind of measurement a claim like this even is. The 3,200 figure is a tangential velocity, the sideways component, the drift across the sky, which makes it a pure Gaia-style measurement, a tiny annual shift in position, multiplied out by the star's distance. That is both its strength and its fragility. Its strength, because sideways motion cannot be mimicked by the tricks that fool radial measurements. No stellar pulsation, no binary companion tugging the spectrum back and forth can fake a star's steady march across the sky. Its fragility, because the conversion from angle to speed leans entirely on the distance. Put the star twice as far away, and the same annual shift means twice the velocity. Bring it closer, and the record evaporates. This is why everything now waits on sharper parallaxes. And notice one more quiet marvel buried in the physics. Whatever launched this star did so without harming it. A slingshot close enough to reach these speeds must skirt the very edge of the zone where tides shred stars, and yet the star sailed through whole. Gravity can do that. It accelerates every atom of a star together, evenly, no strain, no scorch. A star can be thrown at a percent of light speed and never feel a thing. If it carried close-orbiting planets, the calculations say some of those could ride out the throw as well. Whole worlds, taken along on the fastest journey in the local universe. For calibration, set the record holders beside it. The fastest spacecraft humanity has ever flown, the Parker Solar Probe, touches about 190 kilometers per second at its closest sweep past the Sun, and it needed the Sun's own gravity to get there. This star, if confirmed, moves nearly 17 times faster. The interstellar visitors that pass through our solar system, objects like the Comet 3I Atlas, arriving from other star systems, carry speeds of a few tens of kilometers per second. The star outruns them by a factor of 100. Even as 5 HVS-1, the certified champion among main sequence runaways, the star filmed escaping Sagittarius. A star at 1,755 kilometers per second would watch this thing pull away as though it were standing still. The certified record holder outpaced nearly 2-to-1 by an object from a galaxy a fraction the size of ours. If the measurement holds, we are looking at one of the fastest stars ever recorded anywhere in the universe, and it is associated not with the monstrous centre of a giant galaxy, but with the modest cloud next door, and that is precisely the problem. Line up every natural launcher we have met and watch each one fall short. The gentle channels first, gravitational roughhousing inside newborn star clusters, the process that produces most ordinary runaways, tops out for massive stars at a few hundred kilometers per second. Beyond that, the encounters required become so close that stars collide rather than slingshot. Supernova launches, a companion star released when its partner detonates, face the same ceiling for a star like this, and they leave forensic marks besides: contamination from the explosion, a stripped or scorched survivor. This star, by all indications, is clean. Now the heavy artillery, the Hill's mechanism itself, the black hole slingshot, the engine of everything in this story, throws harder as the black hole grows heavier. A 600,000-sun black hole, the launcher our 9 runaways testify to, throws stars at 400, 500, 600 kilometers per second, the speeds we actually observe in the Leo stream. Ask it to produce 3,200, and the mathematics grimaces. You need the binary to skim the black hole at the innermost possible approach on a perfect trajectory, and even then you are straining the tail of what is achievable. The comfortable version of the theory, the one that explains everything else so beautifully, stalls one star short of a complete account. So what could do it? The options on the table are few, and every one of them is remarkable. Option 1, the encounter was simply perfect. The rarest possible geometry, a binary threading the innermost safe distance, the one in many thousands throw. Possible, the way a hole-in-one is possible, uncomfortable as an explanation, because you would prefer not to need a miracle in your first survey. Option 2, the launcher is heavier than 600,000 suns, perhaps considerably, and the 9 gentle escapees are the ordinary throws while this is the occasional full-strength one. That would mean the cloud's monster outweighs every estimate, deepening its invisibility problem. Option 3, and the one theorists keep circling back to, the launcher is not one black hole but 2. A pair of massive black holes orbiting each other forms nature's most powerful slingshot, a rotating gravitational machine that can grip a passing star and hurl it at speeds a single hole cannot approach. Thousands of kilometers per second is exactly the signature a black hole binary writes. And before you dismiss that as exotic, remember what we learned at the crime scene. The Large Magellanic Cloud has been colliding with the Small Magellanic Cloud for hundreds of millions of years, and collisions between galaxies are precisely how central black holes end up paired. If the cloud swallowed a companion's core somewhere in its brawling history, a binary is not a wild idea, it is almost an expectation. Sit with that for a moment. The tidiest explanation for the fastest star in this story may be that the galaxy next door is hiding not one invisible monster but 2, circling each other in the dark. Each option, note, would be a major discovery in its own right. There is no boring resolution left. That is the corner this one candidate star paints us into. Either the universe performed a near-impossible throw, or the hidden black hole is far heavier than believed, or there are 2 of them locked in orbit at the cloud's disturbed heart, or, the possibility we must keep on the table like a 5th card, the measurement dissolves under Gaia's final data release, and the outlier retires quietly the way others have before it. Any of these could be true. All of them are being actively worked on right now. But step back from the single star and look at what we have assembled across this whole investigation. Runaway stars, a hidden launcher, an off-center galaxy, speeds that strain every model. It is time to stop, breathe, and lay the entire case out on the table, because you have now heard every piece of evidence, and you deserve to see what it adds up to before we push into stranger territory still. Part 8. Putting the pieces together. Let us step back and put the pieces together slowly, the way you would lay out a case file on a long table at the end of a long night. We have covered a great deal of ground, And if you have been drifting in and out, this is the place to rejoin. Everything essential is about to pass by one more time. Here is what is measured, beyond reasonable dispute. There exist stars moving too fast for any galaxy to hold. Hypervelocity stars, first caught in 2005, now catalogued by the dozen. The classic sample contains 21 unbound B-type stars in our outer halo. A mechanism predicted in 1988 explains them. A binary star torn apart by a massive black hole, one partner captured, the other flung away, and that mechanism was caught operating red-handed at our own galactic centre when a star was traced mid-flight directly back to Sagittarius A star. All of that is settled science. Then came 2025 and the measurement nobody was ready for. Run the 21 trajectories backward with Gaia's final quality data, and only about 7 return to our galactic centre. Roughly 9 come instead from the Large Magellanic Cloud, the galaxy next door, and the case for what launched them rests on 4 independent legs, each one measured, none of them depending on the others. Leg 1, the tracebacks themselves, 9 flight paths converging on one region inside the cloud. Leg 2, the traffic pattern, those stars pile up on our sky toward the constellation Leo, exactly where objects thrown forward from the cloud's moving platform must land. Nothing random produces that geometry. Leg 3, the speed fingerprint. The cloud's escapees run systematically slower than the galactic centres, 400 to 600 kilometers per second against nearly 900, precisely the gentler throw a lighter black hole must produce. Leg 4, the volume of traffic. The launch rate implied by the sample matches what the slingshot mechanism should achieve at a black hole of a few 100,000 solar masses. 4 legs, 1 conclusion, a black hole of roughly 600,000 suns sitting at the cloud's true centre of gravity, a little over a degree from where the maps draw its middle. Add to the file the character of the scene itself, because it corroborates in a dozen small ways. The Large Magellanic Cloud is not some serene orderly system where a hidden monster would seem out of place. It is a galaxy in mid-collision, brawling with its smaller sibling for the better part of 1 billion years, arriving on what is likely its first pass around the Milky Way, trailing 500 million suns worth of torn loose hydrogen behind it. Its bar is off-centre, its disk is warped, its various centres, the bright one, the gas one, the one its stars actually orbit, disagree with each other by thousands of light years, and the launch point our 9 trajectories identify sits offset from the bright centre by about 1.2 degrees, right in the disturbed zone where the true gravitational anchor of this scrambled galaxy plausibly hides. Even the population inside the cloud cooperates. Gaia finds dozens of runaways still within it, an ejection engine's local exhaust, with one extreme candidate, the 3,200 km per second outlier, waiting at the tail of the distribution like a signature too large for the pen that supposedly wrote it. Against that stands exactly one fact, and it is a heavy one. No instrument has ever detected the object itself. No glow, no X-rays, no radio hum, no orbiting swarm of visible hostages. Every piece of evidence is a star in flight. The entire monster is an inference, a shape drawn around an absence. So how worried should we be about that absence? Here is the honest weighing. Absence of evidence is only evidence of absence when you had a fair chance of seeing the thing, and we have established tool by tool that a starved middleweight in a crowded, scrambled galaxy offers almost nothing to see. The silence is consistent with the theory, but consistent is a lawyer's word, and it is worth remembering the alternatives died on their own faults, not merely by comparison. Supernova launches, wrong speeds, wrong statistics, and they cannot aim. No way to stack 9 stars toward Leo. Cluster roughhousing, ceiling far too low and equally directionless. Chance contamination by ordinary halo stars cannot fake 9 coherent trajectories with a shared origin, a shared traffic pattern, and a shared speed signature. One by one, the mundane suspects fall away, and what remains standing is the invisible one. The suspect whose only alibi is that we should not expect to see it anyway. This is, for what it is worth, exactly how the Sagittarius A star case looked for decades. A compelling inference at the centre of a pattern of motion, waiting nearly half a century for its photograph. Patterns first, portrait later. The cloud may simply be earlier in the same story. It is also worth stating plainly what would change the verdict, because a case you cannot imagine losing is not science. It is faith wearing a lab coat. If Gaia's final data release revises the proper motions and the 9 trajectories stop converging, the black hole dissolves. If deeper surveys find the LEO clustering was a statistical accident of a small sample, the traffic pattern leg breaks. If someone measures the stellar motions at the offset point with next-generation instruments and finds no rise in speeds, no kingdom, no king, then the silence stops being consistent and starts being damning. Every leg of this case is scheduled for cross-examination within a few years, and that is precisely what makes it worth caring about. This is not a mystery that will drift unresolved for a century. It is a mystery with court dates, and pause, briefly, on what a conviction would actually mean, because the stakes reach well past one galaxy. Confirm the cloud's black hole, and it becomes the nearest massive black hole beyond the Milky Way, a laboratory specimen sitting on our doorstep, in the one dwarf galaxy we can study star by star. It becomes one of the only known residents of the intermediate mass desert, the missing middle of the entire black hole census. And it becomes the founding entry in a ledger astronomy has never opened, the census of sleeping black holes in dwarf galaxies, a population that plausibly numbers in the billions across the universe. If you like, take a moment to picture the state of things tonight as you listen. The southern sky is up somewhere in the world right now. The cloud is there, glowing faintly over some quiet stretch of ocean, looking exactly as it looked to Magellan's sailors and to the first humans who ever crossed into the southern hemisphere. Nothing about it appears to have changed, and scattered through our halo, 9 blue stars are climbing away from it at 500,000 kilometers per second, carrying the only testimony that something enormous is sleeping inside. The sky, it turns out, has been holding a sealed envelope over our heads for a very long time. We have only just learned how to steam it open. But a case built entirely on inference has one soft spot, and a careful mind should press on it. Everything we have concluded assumes that when stars are thrown, gravity did the throwing, because gravity is the only thrower we know. The stars themselves testify only to their speeds and their origins. They do not testify to the engine, and there is a wider ledger we have not yet opened, one that catalogues every star ever thrown out of every galaxy. A ledger written in light, spread across the spaces between galaxies, going back nearly to the beginning of time. If galaxies have been flinging stars into the void for 13 billion years, the void should be keeping receipts. When astronomers finally read that ledger properly, with the James Webb Space Telescope peering at galaxy clusters as they were when the universe was young, they found something quietly, deeply wrong with the accounting. The receipts are there. But they do not add up the way the ejection story says they should, and that discrepancy, patient, statistical, easy to miss, is where this investigation turns from one hidden object in one small galaxy to a question about the entire universe. Part 9. The Missing Starlight. Begin with the prediction, because it seems airtight. Galaxies throw stars away. We have now watched them do it. Our galaxy does it, the cloud does it, and if the story we have assembled is right, dwarf galaxies across the universe have been doing it since nearly the beginning. The universe is 13.8 billion years old. Multiply a slow, steady leak by all of that time, across 2 trillion galaxies, and the conclusion writes itself. The spaces between galaxies should be slowly filling with exiled stars, and crucially, the filling should be cumulative. An old cluster of galaxies has been leaking for longer than a young one, so older neighbourhoods should sit inside visibly thicker fogs of escaped starlight. Ejection is a tap left running. The longer the tap runs, the higher the water. Find the waterline, and you confirm the whole picture. Every hypervelocity star ever thrown becomes one drop in a rising readable tide. The remarkable thing is that the water exists and we can see it. Point a sensitive telescope at a great cluster of galaxies, hundreds or thousands of galaxies swarming in a shared gravitational well, and look away from the galaxies themselves at the supposedly empty space between them. It is not black. There is a glow there, faint, smooth, enormous, filling the cluster like mist in a valley. Astronomers call it intracluster light, and it is made of stars that belong to no galaxy at all, orbiting the cluster itself, alone, and there is nothing marginal about the population. In mature clusters, this homeless light amounts to 10, 20, in some cases 30% of all the starlight the cluster produces. Count it up, and the numbers stop feeling like astronomy and start feeling like a misprint. Trillions of stars in a single cluster with no galaxy to call home. Summed across the universe by some estimates, something approaching 1 star in every 10 is adrift between galaxies. Stand back from that. The universe's galaxies, the grand structures we name and catalogue and photograph, do not even contain all the stars. 1/10 of everything drifts in the dark between them. Stay with that dark for a moment and go there. Imagine yourself on a world orbiting one of these exiled suns, far out in intra-cluster space. Night falls, and the sky is wrong. There are no stars, not one. Your sun's nearest stellar neighbour is not 4 light-years away as ours is, but thousands, far too distant for any planet-bound eye to see. Where constellations should hang, there is only black, and scattered across the black, a handful of faint fuzzy ovals, entire galaxies, each one holding hundreds of billions of suns, each utterly out of reach. From your world, astronomy would be a science of smudges. No Milky Way arching overhead, no North Star to navigate by, no sense anywhere in the sky that suns come in crowds. If civilizations arise on such worlds, they may take far longer to learn what a star even is. Their own is the only one they will ever see as more than a mathematical point in someone's telescope. This is the ocean the exiles sail into. This is where every thrown star is bound. So the glow is real, and the reservoir is enormous. Now comes the accounting problem, the quiet contradiction this chapter exists to deliver. If steady ejection over cosmic time were a major contributor to that glow, the mathematics of a running tap applies. Older systems, more water. Young clusters, seen early in cosmic history, should show thin, patchy intracluster light. Ancient ones should be flooded. That gradient is the fingerprint the ejection story requires, and for decades we could not check it because the glow is brutally faint and the young clusters are brutally far away. Seeing them means seeing across most of the universe's history. Then the James Webb Space Telescope arrived, with exactly the infrared reach and raw sensitivity the problem demanded. In 2022, it mapped the ghost light in a cluster called SMACS 0723 out to distances no ground-based telescope had managed. And soon after, astronomers pushed the technique to clusters at redshift beyond 1. Systems whose light left them when the universe was less than half its current age, adolescent structures still visibly under construction. If the tap theory is right, these young clusters should be nearly dry. Appreciate briefly how hard this measurement is, because it explains why the answer took until now. The ghost light is faint beyond ordinary intuition, hundreds of times dimmer than the natural glow of Earth's own night sky, which is why ground-based attempts spent decades fighting their own atmosphere. It is smooth and structureless, so any stray light in the telescope, a bright star's halo, reflections in the optics, can counterfeit it. And at great distances there is a crueler tax. The expansion of the universe itself dims extended glows ferociously, so the farther back in time you look, the harder the ghost is to see, precisely where the tap theory most needs checking. This is why Webb mattered. Parked in deep space with no atmosphere, no stray moonlight, and exquisite infrared sensitivity, it could finally photograph the fog in young clusters directly rather than arguing about it statistically. The question had waited half a century mostly for an instrument that could survive asking it. They are not dry. That is the result, and its size is worth saying plainly. In these adolescent clusters seen 10 billion years ago, the homeless starlight is already there, abundant, smooth, and fully established, averaging around 17% of the total light. 17% when the universe was young, statistically indistinguishable from the fractions we measure in ancient present-day clusters. A 2023 study in the journal Nature laid it out across seminal samples of early clusters, and the conclusion has only firmed since. There is no rising waterline. The fog does not thicken with age. The glow between galaxies appears early, arrives at its full strength almost immediately, and then simply persists, indifferent to the billions of years of stellar ejection that follow. Every hypervelocity star thrown since the universe's youth has vanished into a background that shows no sign of receiving them. The tap has been running for 13 billion years, and the water level has not visibly moved. What does that mean? The mainstream resolution is elegant, and it survives every test so far. The glow was never made by the tap. It was made by violence, sudden, wholesale violence, early and huge. When galaxies merge, tides strip entire outer layers of stars in single events, spilling billions of suns at once. When small galaxies fall into growing clusters, they are shredded on the way in, dissolving into the shared gravity like sugar in water. The construction era of clusters, the crowded, collision-rich first few billion years, was precisely when this stripping ran hottest, which is why the ghost light appears early and fully formed. The forensics agree. The colours and chemistry of intracluster stars match the stripped outskirts of galaxies, not the dense central neighbourhoods that black hole slingshots sample, and the arithmetic settles any doubt about proportion. Our galaxy ejects roughly one hypervelocity star every 10,000 to 100,000 years. Run that rate for the entire age of the universe, and you accumulate perhaps 1 million exiles, against the hundreds of billions of stripped stars in a single cluster's glow. The ejection channel is real, but it is a teaspoon poured into a sea that was filled by tidal waves. There is even an independent ceiling confirming nothing big is hiding. The New Horizons spacecraft, drifting beyond Pluto in skies dark enough for the measurement, has weighed the universe's total visible light, and it roughly matches what the known galaxies and known diffuse sources produce. There is no great unexplained surplus of homeless starlight, and no room for one. So the ledger balances after all. But notice what the balancing costs us emotionally, because this is where the accounting turns cold. The exiles do not matter. That is what the numbers say. Every star the cloud's hidden black hole has ever thrown, every runaway our own centre has launched, every hypervelocity star in every survey. Cosmically, they amount to nothing measurable, and they will never arrive anywhere. Run the travel times. A star leaving the Milky Way at 700 kilometers per second would need well over 1 trillion years to cross to the Andromeda Galaxy, more than 80 times the current age of the universe. A B-type star lives a few 100 million years. The arithmetic is not close. The star dies less than 1,000th of the way into the crossing, and its cooling remnant sails on. A dead ember drifting through darkness that literally never ends, its journey unfinished when the last stars in every galaxy have burned out. Some of these exiles, remember, may carry planets, worlds that formed in the bright, crowded heart of a galaxy, now bound for a place where the sky holds nothing at all. Every ejection we have described tonight, every elegant slingshot, is a sentence with no possibility of parole. Out, alone, forever, arriving nowhere. The launcher next door is feeding a sea it can never fill, one permanent goodbye at a time. Our own neighbourhood keeps a modest version of the same fog, by the way. This is not only a story about distant clusters. The local group, our small gathering of galaxies, is expected to hold its own thin population of intragroup stars, shed during the long gravitational acquaintance of the Milky Way Andromeda and their dozens of satellites, and candidate homeless stars have indeed been reported drifting in the space between us and Andromeda. The 9 runaways from the cloud are, in the most literal sense, joining that population as we speak, the newest residents of the emptiest address there is. In a few 100 million years they will be dark, cold, and beyond every survey, indistinguishable from the ancient exiles around them. The fog absorbs everything and acknowledges nothing. Unless, of course, you're willing to entertain a stranger thought. There is a reading of this ledger, not the mainstream one, not the one the evidence favours, but one that genuinely circulates in serious speculative literature, under which the missing accumulation is not an accounting subtlety at all. Under this reading, the thrown stars fail to pile up in the void for the simplest possible reason: they are not being thrown away, they are being sent somewhere. And to entertain that thought honestly, which we are about to do, with every safety label attached, we need to talk about machines the size of stars. Part 10. The Engine Hypothesis. Let us be completely clear about where we now stand, because this channel keeps an honest border between what is measured and what is imagined, and we're about to cross it. Everything up to this point has been evidence, measured speeds, traced trajectories, published statistics. What follows in this chapter is speculation, documented, physically literate speculation that real scientists have taken seriously enough to define and test, but speculation all the same. The mainstream explanation for everything we have seen remains the hidden black hole, and by the end of this chapter you will see that the mainstream explanation wins on the data. But you deserve to hear the strange idea properly, because it was born from a fair question, the exact question this investigation keeps circling. Every conclusion we have drawn rests on one assumption so fundamental we never said it out loud, that when a star is thrown, gravity did the throwing. The launcher in the cloud is inferred, not seen. Nobody has ever laid eyes on it. So a small number of thinkers have asked in all seriousness, what else, in principle, can move a star? And the unsettling truth is that physics has an answer. Physics has had the answer for decades. The answer is called a stellar engine, a machine or a swarm of machines built around a star to harvest its own output and convert it into thrust, moving the star and everything orbiting it through space on purpose. This is not a fever dream from a comment section. It lives in the peer-reviewed speculative engineering literature, complete with a formal classification scheme worked out by the physicist Viorel Badescu and the engineer Richard Cathcart, dividing the designs into classes by ambition. And before your skepticism dismisses the whole idea as impossible, a reasonable reflex, notice that the simplest design requires no exotic physics whatsoever. It requires only patience, mirrors, and an uncomfortable fact you already know. Light pushes. Class A is the classic, proposed by the physicist Leonid Shkadov back in 1987, by coincidence, 1 year before Jack Hills worked out the natural slingshot. The Shkadov thruster is, at heart, a mirror, a colossal, feather-light reflective shell, hovering on one side of a star, held in place not by orbiting but by balance, the star's gravity pulling it in, the star's radiation pressure pushing it out, the two cancelling so the mirror simply floats. And a floating mirror does something profound. An ordinary star radiates equally in all directions, and all those light pushes cancel. The star goes nowhere. But hang a mirror on one side, bounce some of the light back, and the symmetry breaks. More light ultimately leaves in one direction than the other, and light carries momentum so the star recoils, gently, endlessly, in the direction the mirror shades. The star becomes its own rocket, burning nothing extra, pushed by its own shine. The acceleration is comically small. For a star like the Sun, the full effect works out to a few dozen light-years of displacement after 1 billion years. But it never stops, it never refuels, and given tens of millions of years it bends a star's course meaningfully. Here is the detail that makes this chapter genuinely eerie rather than merely fun. The Shkadov thrust scales with the star's brightness. Luminous stars make the best engines. The thrust is larger, and their shorter lives matter less on engineering timescales. And the hypervelocity stars filling this story are B-type stars, hot, blue, and hundreds of times more luminous than the Sun. If you were shopping for stars to move, you would shop for exactly the class of star we keep catching in flight. Coincidence? Surely. But the kind a good detective writes down. Class B improves the mirror into an optical system, a partial shell that gathers the star's output and beams it, concentrated in a chosen direction. A searchlight with a sun for a bulb. More thrust, and steerable. Class C stops pushing light around and starts moving matter. The modern benchmark was worked out in 2019 by the astrophysicist Matthew Kaplan. Machinery that skims material off the star itself, lifted by magnetic fields, boiled off by directed beams, and fires it as exhaust at ferocious speeds. The star becomes a true rocket, spending its own substance for thrust. Kaplan's calculation suggests such an engine could move the Sun about 50 light-years in 1 million years, thousands of times faster progressed than the mirror, using engineering that breaks no law of physics, merely every budget any civilization has ever imagined. Scale the design up, run it for tens of millions of years on a luminous star, and speeds in the hundreds of kilometers per second stop being unthinkable, and become, on paper, a procurement problem. The Class C family runs deeper than the single benchmark, and the variants are worth a glance just to appreciate how much room the physics leaves. One version lifts hydrogen off the star and fuses it in external reactors, expelling the products as exhaust. The star used as a fuel depot rather than an engine, its lifetime actually extended by the skimming, because lighter stars burn slower. Another rides the star's own wind, enormous magnetic sails, coupling to the charged particles every star constantly sheds, tacking against the stellar breeze the way ships tack against the sea. At the far end of ambition, the star is not the vehicle at all, but the power plant, its output driving some larger propulsion system that carries planets and habitats alongside, a solar system moved as a single household. None of these violates a conservation law. All of them merely require construction on a scale that makes planetary engineering look like carpentry. That is the consistent, humbling message of this literature. The universe does not forbid moving stars. It only prices the ticket beyond anything we can currently imagine paying. Why would anyone move a star? The speculative literature has never lacked motives. To escape a doomed neighborhood, a coming galactic collision, an active galactic nucleus about to sterilize its surroundings, to gather resources on timescales where stars are the only durable vehicles, to rearrange a galaxy's assets the way we rearrange rivers, and notice, the pattern matching is irresistible, which is exactly why it must be handled with tongs. The Large Magellanic Cloud fits the brochure suspiciously well, a gas-rich galaxy, furiously forging the luminous stars that make the best engines, currently being dragged into a collision with a galaxy 10 times its size. If you were a civilization living there, you would know what is coming, and under the full version of the speculation, the missing starlight ledger stops being a contradiction and becomes a shipping manifest. The stars leaving the cloud are not exiles accumulating in the void. They are deliveries, aimed at destinations, and the reason the intergalactic fog never thickens is that the cargo does not linger in transit space. The hypervelocity stars in this reading are not evidence of a black hole, they are traffic. Before the verdict, one fair word about why serious scientists engage with any of this instead of laughing it out of the room. The modern search for what researchers call technosignatures treats questions like this one as legitimate science for a simple reason. They are falsifiable, and their null results teach. Every time an anomaly like the clouds gets a clean natural explanation, we learn precisely how easily nature imitates purpose, how many ways gravity, dust, and statistics can conspire to look deliberate. That calibration is the only way we would ever recognize the real thing should it exist. The researchers who define stellar engines are not claiming anyone has built one. They are drawing up the wanted poster in advance, so that if the universe ever shows us one, we will know its face. It is a gorgeous story. Now let us do what this channel does and hold it up against the data, because the stellar engine hypothesis, to its credit, is not unfalsifiable hand-waving. It makes concrete predictions, and every one of them can be checked. Prediction 1, waste heat. This is the deepest test, courtesy of Freeman Dyson, who pointed out in 1960 that thermodynamics is the one law no engineering can evade. Any machine harvesting a star's output must re-radiate its waste as infrared warmth. A star wearing an engine should glow wrong, an infrared excess, possibly lopsided, that ordinary stars do not show. The hypervelocity stars have spectra and photometry on file. None shows an anomalous infrared signature. The exhaust is missing. Prediction 2. Powered flight. An engine pushes continuously, so a driven star's path should bend away from a pure gravitational trajectory, the exact thing our forensics can now detect. But the tracebacks are the whole reason this story exists. The runaways fit ballistic, unpowered flight through known gravity so well that we use them to locate their launcher. Ballistic is the opposite of driven. Prediction 3. Engineering scars, strange chemical abundances, odd variability, the fingerprints of a worked star. The runaways are spectroscopically, boringly normal B-type stars, clean on all three counts, and the wider searches say the same. A project called Hephaestus combed through the infrared signatures of roughly 5 million stars from Gaia and allied surveys, hunting for exactly the waste heat glow a Dyson-style structure cannot hide. It found 7 ambiguous candidates out of 5 million, and follow-up work has attributed most of those to mundane contamination, distant dusty galaxies photobombing the measurements. Remember too the cautionary tale this field already lived through. When Tabby's star began its bizarre, irregular dimming in 2015, the megastructure hypothesis went mainstream for one giddy year, until careful monitoring showed the dimming was stronger in blue light than red. Solid structures block all colours equally. Dust does not. It was dust. The lesson was not that the question was foolish. The lesson was the order of operations. Anomaly first, exhaustive natural explanations. Second, aliens last, and only if something survives. Here, nothing survives. Even the romantic core of the idea, the delivery network, dies on simple arithmetic we have already done. At these speeds, an intergalactic crossing takes 1 trillion years, and the starships die 1,000th of the way there. You cannot run a shipping line whose cargo expires 10,000 times over in transit. Whatever the Large Magellanic Cloud is doing, it is not exporting stars to anywhere that matters. So the verdict, honestly rendered, on one side, a black hole, unseen, yes, but demanded by 4 independent lines of quantitative evidence, consistent with every null detection and matching a class of object we have found elsewhere by identical methods. On the other, engines, unseen and contradicted by the infrared data, the ballistic trajectories, the clean spectra, the null surveys, and the travel time arithmetic. One hypothesis is invisible but has physics quietly voting for it everywhere you check. The other is invisible and keeps losing every vote taken. That asymmetry is the whole difference between a mystery and a fantasy. And this story remains magnificently a mystery. Because the honest scorecard still ends on the honest fact. The object that wins the verdict has never actually been seen. A court can convict on circumstantial evidence, but astronomy eventually demands the photograph. So how do we get it? How do you catch a monster that emits nothing in a galaxy next door before the whole field moves on? It turns out there is a plan, several plans, and some of them are already running tonight. Part 11. The Hunt. Remember the line we planted near the beginning of this investigation? You can learn a lot about something by watching what runs away from it. When it first appeared, it was a forensic observation, a wry summary of how 9 fleeing stars betrayed a hidden monster. But listen to it again now, at the far end of the case, and notice that it has quietly changed jobs. It is no longer a description of what happened. It is the blueprint for what happens next, because essentially every plan now in motion to confirm or kill the cloud's black hole is, in one form or another, a more careful way of watching what runs away. The joke became the method. The field's entire toolkit is now organized around reading departures. Over the next handful of years, that method gets its greatest tests, and this chapter is about what specifically is coming, because one of the rarest gifts a scientific mystery can offer is a schedule. The first court date belongs to Gaia, the mission that is somehow not finished producing revolutions from beyond the grave. The spacecraft itself has been silent since early 2025, but its final archive is still being distilled, and data release 4 is expected at the end of 2026. This is not a routine update. It will roughly double the time baseline of the measurements, and for delicate proper motions, a doubled baseline does not merely double the quality. Errors shrink dramatically as a drift is tracked over more years, the way a trend line firms up with every added season of data. Consider what that does to this case. The handful of runaways currently labelled ambiguous, too uncertain to assign to either launcher, should snap into focus, flipping decisively toward the Milky Way's centre or toward the cloud. Each flip is a new vote. If most break toward the cloud, the launch rate rises and the case hardens. If the tracebacks tighten and the convergence point sharpens, the black hole's location gets pinned to a smaller and smaller patch of that offset zone, and the 3,200 outlier faces its own reckoning. Better parallax, better proper motion, verdict delivered. Either the record-breaking speed survives, and the binary black hole conversation begins in earnest, or it dissolves into measurement error and retires, as other extreme candidates have before it. Both outcomes teach. That is the beauty of this stage of the story. From here forward, every result is informative. The case can no longer stall, it can only move. The second court date is continuous. It is running tonight, on a mountaintop in Chile. The Vera Rubin Observatory has begun its decade-long survey of the entire southern sky, photographing it again and again every few nights with the largest digital camera ever built. Rubin is a machine designed to notice change. Anything that flares, dims, moves, or appears is flagged automatically, night after night, across the whole sky at once. Now recall the one meal a starving black hole cannot refuse. Every so often, perhaps once in 10,000 years, perhaps once in 100,000 for an object like the clouds, an unlucky star wanders too close and is torn apart, and the debris, spiraling in, ignites a flare that burns for months. Astronomers call it a tidal disruption event, and it is the one moment a perfectly dark black hole is forced to introduce itself. The odds on any given year are long, that is honesty. But the Large Magellanic Cloud sits squarely in Rubin's field, and Rubin does not blink, and the wager costs nothing. The survey is running anyway for 1,000 other reasons across 10 full years, watching the cloud along with everything else in the southern sky. If the monster feeds even once while the camera watches, The mystery ends overnight. A flare erupting at the exact coordinates the runaways predicted would be the single most satisfying confirmation in modern astrophysics, an X on the map, drawn by the fleeing stars and signed at last by the monster itself. Alongside the space missions, the ground is working too, in the unglamorous way that actually closes cases. The runaway sample itself is being re-interviewed. Spectroscopic campaigns are refreshing the radial velocities of the known hypervelocity stars that toward and away half of their motion, because a trajectory is only as good as its weakest measured dimension, and some of these stars have not had their spectra retaken since the era when everyone already knew where they came from. Sharper radial velocities plus the final Gaia-proper motions means each traceback becomes a genuinely three-dimensional flight path with honest error bars, and the convergence test becomes merciless. Meanwhile, the next generation of wide-field spectroscopic surveys is coming online across both hemispheres, industrializing the discovery process that once required a lone astronomer feeding blue stars through a telescope one at a time. The original survey found 21 unbound stars by examining a careful slice of sky. The coming surveys will measure millions of stars per year. If the cloud has been launching stars for eons, the halo should be seeded with fainter, older escapees no one has yet catalogued, and every single one found is another line drawn backward toward the launcher. The sample that started this story fit on a single page. The sample that ends it may fill a database. The third approach is the patient one. Go look at the kingdom. A 600,000-sun black hole rules a sphere of influence a few light-years across, and inside that sphere stars must orbit fast, speeds rising steeply toward the center, the same signature that convicted Sagittarius A star and the Omega Centauri middleweight. At the cloud's distance, resolving that kingdom strains today's instruments, but a new generation is arriving. In the Chilean Andes, the extremely large telescope is nearing completion, with a mirror 39 meters across, collecting more light than every previous large research telescope combined, and adaptive optics sharp enough to pick individual stars out of exactly the kind of crowded field that has protected the cloud's secret. Point instruments like that at the offset zone measure a few thousand stellar velocities, and the question stops being philosophical. Either the speeds rise toward a dark point, a kingdom, and therefore a king, or they do not. There is also a subtler geometric trick available in the meantime, one of those ideas so clean it feels like cheating. Use the launcher against itself. Every newly discovered runaway adds another line pointing backward. Triangulation improves with every star. The monster cannot stop broadcasting its address because broadcasting is what throwing stars is. The very behavior that keeps it fed keeps it findable, and the story does not end at the cloud, whichever way the verdict falls. If the black hole is confirmed, it instantly becomes the nearest massive black hole beyond our galaxy, and the founding member of a census astronomy has never managed to take, and the search turns immediately to every other dwarf galaxy in reach. The small Magellanic Cloud, the cloud's battered sibling, does it keep its own sleeper? The dwarf spheroidals, Fornax, Sculptor, and their dim kin scattered through our halo. Do fast stars leak from them too? Too few and faint for past surveys, but not for the next ones. Every dwarf galaxy in the sky becomes a sealed envelope, and we now know the steaming technique. If, instead, the black hole is refuted, if the final data release unravels the tracebacks, the alternative is not comfort. It is a set of the fastest stars ever measured, with a coherent traffic pattern and a speed fingerprint and no launcher at all. Explaining that would require something genuinely new, and the universe would be a measurably stranger place than the one where the monster simply exists. There is no boring ending left. There has not been one for some time. Step back once more and notice what you are actually witnessing, because it is easy to miss from inside. You happen to be alive during the short window in which this gets answered. Most cosmic mysteries do not offer that. Consider the track record of questions like this one. The reality of black holes themselves hung unresolved for half a century between Einstein's equations and the first convincing candidates. Sagittarius A star waited 48 years between first detection and first photograph. Gravitational waves were predicted in 1916 and heard in 2015, a 99-year wait. Planets around other stars were debated for centuries and confirmed only in the 1990s. Astronomy's deepest questions usually outlive the people who ask them. That is the normal shape of this science. The cloud's black hole has jumped the queue. The great questions of astronomy tend to operate on timescales that mock human lifetimes, but this one has instruments already built, surveys already running, and a data release already scheduled. The people who will settle it are working tonight. Within a decade, perhaps within a few years, either a photograph, a flare, or a velocity map will end the argument, and the textbooks will be rewritten again in whichever direction the sky insists. And here is the final turn of this story. The reason the ending is not really an ending. Whatever that verdict says, it describes an object that is not staying where it is. The galaxy next door is not merely sitting in our southern sky posing for confirmation, it is falling, and the thing it carries, seen or unseen, proven or not, is coming here. Part 12. The Collision Course. Everything we have described tonight, the fleeing stars, the hidden launcher, the offset center, the long wait for a photograph, is happening on a collision course. The Large Magellanic Cloud is not in a stable orbit around the Milky Way. It cannot be. It is too heavy, and it is too close, and gravity keeps accounts on everything. Each time a satellite galaxy plows through a larger galaxy's halo of dark matter and scattered stars, it raises a wake behind itself, a gravitational bow wave of disturbed material, and that wake pulls backward on the satellite like water dragging on a swimmer. Astronomers call the process dynamical friction, and it is patient beyond all human meaning, and it only ever works in one direction. Orbit by orbit, the cloud must lose energy, and its path must decay, and the endpoint is not negotiable. The simulations that track this carefully, accounting for the cloud's surprising heft, its first passage trajectory, the Milky Way's response, converge on a timeline. In roughly 2.4 billion years, the Large Magellanic Cloud will spiral in, break apart, and merge with the Milky Way. Long before Andromeda arrives for its more famous appointment, we will have absorbed the galaxy next door. The neighbour is moving in. Set the appointment in its calendar properly, because the neighbourhood has more than one. The famous collision, the one documentaries dwell on, is Andromeda's, the great spiral 2.5 million light-years away, closing with the Milky Way for a merger some 4 to 5 billion years out, the event that will eventually fuse the local group's two giants into a single enormous galaxy. The cloud's appointment comes first, by roughly 2 billion years. Our galaxy, it turns out, has a warm-up act. Before we merge with an equal, we will absorb a companion a tenth our size, and the absorption will rehearse. In miniature, everything the larger collision later performs, the stripped streams, the fresh starbursts, the black holes spiraling to the centre. Galaxies grow this way as a rule. Our own halo already carries the fossil streams of a dozen smaller meals, and the cloud is simply the next and largest item on the menu. There is nothing exceptional about the process. What is exceptional is the timing of our seat. Close enough to watch the approach, early enough that the evidence, the runaways, the stream, the wake in the halo, is all still fresh and readable. Understand what a galactic merger actually is, because the phrase suggests a catastrophe, and the reality is stranger and quieter. Stars do not collide. They are too small and too far apart. Entire galaxies pass through one another, with essentially no stellar impacts at all. What merges is structure. The cloud's careful anatomy, its off-center bar, its warped disk, its star-forming districts, will be stretched, sheared, and unwound by tides until nothing remembers its original shape. Its billions of stars will be spilled into our halo in great looping streams, the way sugar pours into water, and over a few billion years the streams themselves will fade into the general population. Its gas, all that raw material the tarantula has been burning through, will rain into the Milky Way and touch off a final generation of new stars wearing Magellanic chemistry. The Magellanic Stream, that half-billion sun ribbon of torn hydrogen, will be swallowed whole, and when it's over, the southern sky's soft glowing patch will simply be gone, its contents redistributed, anonymous, ours. Astronomers of that era, if any exist, will find the evidence only the way we find our galaxy's older meals, as chemical fingerprints and fossil streams, the faint bookkeeping of a galaxy that used to be. But one part of the cloud will not dissolve into anonymity, and it is the part this entire investigation has been circling. A 600,000-sun black hole cannot be unwound by tides or scattered into streams. It is too dense, too compact, too finished. When its host galaxy comes apart around it, the black hole will simply keep going, naked now, orphaned, falling inward through the wreckage of its former home, and dynamical friction, the same patient drag that doomed the cloud, will go to work on the black hole itself. Massive objects moving through fields of stars always sink. The physics offers no other option. Over hundreds of millions of years, the orphan will spiral down through the Milky Way's body toward the one address every sinking mass eventually reaches, the exact center where something is waiting: Sagittarius. A star, 4.3 million solar masses, our own resident monster, sits at the bottom of the galaxy's gravitational well, and the cloud's black hole will be delivered to it as inevitably as a dropped stone finds the bottom of a lake. The two will bind into orbit, tighten over ages, and finally merge, an event that will shake space-time itself, radiating gravitational waves detectable, in principle, across most of the observable universe. Our galaxy's black hole will swallow the clouds and grow and settle. And if that infall stirs the surrounding gas, as such upheavals often do, the Milky Way's quiet center may light up for a time as an active nucleus, our sleepy monster, woken by its meal, announcing the acquisition to the cosmos. The object nobody can find today may end its story as the brightest thing in the galaxy. There is even a fitting postscript for the instruments: mergers between black holes of exactly these masses, hundreds of thousands to millions of suns, ring space-time at the low, slow frequencies that space-based gravitational wave observatories now under construction are being designed to hear. The detectors humanity is building this century listen for precisely the chord that our galaxy's far future will strike. Civilizations elsewhere, with older instruments and better seats, may hear such chords routinely. The standard closing note, sounded whenever any galaxy anywhere finishes absorbing a neighbor. Stand on Earth then, or on whatever ground exists here, 2.4 billion years from now, and watch the arrival. The cloud no longer sits politely in the southern sky, as a smudge you could cover with your palm. It sprawls across the heavens, torn into luminous arcs that span horizon to horizon, its star streams braiding into the Milky Way's own band until the two galaxies are a single tangled sky. New stars are igniting everywhere in the infalling gas, brilliant short-lived blues burning in clusters that did not exist a million years earlier. There is no roar, no impact, no moment of collision to point to. The spectacle unfolds at the pace of continents drifting, and only a time-lapse across a million human lifetimes would reveal the motion at all. And somewhere behind all that light, invisible even now, two black holes are closing their long spiral. The found and the unfound, the photographed and the inferred, tightening toward each other at the center of the merged sky. No one watching will see them. They will know they are there, if anyone is left to know anything, the same way we know tonight, by watching how everything else moves. It is worth being honest about the audience too. 2.4 billion years is roughly half the remaining lifetime of a warming sun that will by then have likely boiled Earth's oceans away. The merger is real, and the appointment is kept, whether or not anyone here keeps it. You, listening tonight, may be as close to a witness as this event ever gets, seeing it in advance by arithmetic from the one era in which its opening act happens to be observable. And there is something almost unbearably calm about that, which is why it belongs at the end of a night like this. Nothing in this story is a threat. The stars fleeing the cloud will not strike us. Space is too empty, and their courses miss everything. The merger will not shatter worlds. It will pour one galaxy gently into another over spans no clock we own can feel. The two black holes will meet and merge without disturbing a single sleeping person anywhere. These are simply the largest events in our corner of the universe proceeding, indifferent, unhurried, on schedules that make every human concern a rounding error. All of history, every civilization, every life, fits into a sliver of the time this one appointment has already spent in transit. There is a strange comfort in that scale, the same comfort this channel returns to again and again. The universe is not waiting on us, and its patience is total, and tonight, under whichever sky you are falling asleep, the machinery is turning exactly as it should. So end where the evidence ends, with the runaways themselves. They are still out there tonight, 9 blue stars climbing through the halo, and the outcast far ahead of them, and somewhere, perhaps, one impossible outlier doing 3,000 kilometers every second, each of them carrying in its speed and course the only testimony we possess about the thing that threw it. They will outlast the question. Long after the cloud has dissolved and the black holes have merged and the merged galaxy has settled into some new calm, the exiles will still be sailing outward through the dark between the galaxies, unreachable and unrecalled, the flung evidence of a crime the universe already quietly solved. We began tonight with a simple claim. You can learn a lot about something by watching what runs away from it. Here, at the end, you can see how much that turned out to mean. The most honest map of the universe is drawn not from what shines, but from what moves, and half of what moves, it now seems, answers to things no one has ever seen. No one was ready for what came out of the galaxy next door, and the thing that threw it, patient, silent, and heavier than 500,000 suns, is already on its way to meet us.